Hi, I'm Meta Spencer. Today I'm going to go to Nevada and talk to a guy who's an expert on clouds. And he not only is an expert on clouds in general, but specifically on cirrus clouds, which are those high things, really, really, really high, and they have ice in them. And they're like a blanket that keeps the warmth in the earth. And he thought up this idea, which people are now exploring, that you could just poke a hole in the blanket and let some of the heat out. And that's the way I think of it. I don't think he's described it that way. But anyway, I've talked to him before. So his name is David Mitchell. And he's going to tell us about his idea again and where it stands. Because people keep, experimenting and doing research. Not as much as they should, though. They really ought to get onto this one. And in Ottawa is a regular, an old friend of mine, Paul Beckwith, who has his own show. He talks about once a week, if not more, on a YouTube broadcasting thing about climate. And he's always explaining climate to people. Hello, David, and hello, Paul.
Hi.
Hi.
Okay, and David, I want you to get us going, because you just mentioned that you have a new a show that you put together because Desert Research Institute, where you work in Nevada, wanted somebody to put a simplified explanation out, and you made something. So why don't you show us a little bit about what you have already shown to the world recently?
This cirrus cloud idea is relevant mostly to the polar regions because you don't want a lot of sunlight involved if you're trying to cool the planet. And the idea, like you said, poke a hole in the blanket and let the heat out. It's working with thermal radiation, long wave radiation, terrestrial radiation, some people call it. So the Earth is giving off heat. And
hold on, wait a minute. Let me make sure I understand. Long wave radiation, that is, there's infrared or something like that, and then there's
that's right. That's long wave.
That's long wave. Okay.
Yeah.
All right. Go on.
So the greenhouse gases are trapping the long wave radiation, and that's why we have this problem. They're not reflecting sunlight. They're absorbing the heat given off by the Earth for long wave radiation, and they re-emit it back to the Earth, and that's the greenhouse effect. And cirrus clouds do that too. All clouds do that to some extent. But the cirrus clouds have a stronger greenhouse effect than the other clouds do. So if you could reduce their lifetime and make them thinner, you could allow some of that long wave radiation, thermal radiation, to escape to outer space. That's like the poking the hole in the blanket idea. The first concept is cirrus clouds themselves. They're clouds that are pure ice clouds. They're formed at a temperature colder than minus 38 degrees Celsius. It's roughly minus 40 degrees Fahrenheit as well. These ice crystals that are formed in cirrus clouds occur or are produced through two mechanisms. One of them is called heterogeneous ice nucleation, and the other is homogeneous ice nucleation. So these are basically two physical pathways through which the ice is produced. And if we were able to make these clouds thinner and reduce their lifetimes, the homogeneous ice nucleation process would need to be pretty important. Maybe, contributing half of the radiative effect of the cloud, for example. So that's what's unknown.
What's the difference between the homo and the hetero?
Yeah, so the heterogeneous process forms ice on what they call an ice nuclei. It's a special particle that has a hexagonal structure similar to an ice crystal. That's one way, at least. So you can think of it like that, like the crystal structure is similar to ice on these ice nuclei. And there's very, very few of those particles. When you consider all the aerosol particles in the atmosphere, these ice nuclei are a small subset of the total population of tiny particles called aerosol. But you can form ice crystals on them. That's one pathway. The other pathway is called homogeneous ice nucleation, and they're formed on solution droplets that don't involve a particle. So it could be tiny haze droplets that are aqueous, having no particle, solution droplets. They're like usually less than a micron or a few microns. And then there's cloud droplets too that can freeze homogeneously without a particle. So one of them is the heterogeneous nucleation process. We know that happens. Anytime you form a cirrus cloud, you have to have that process. But at a certain, what they call relative humidity inside the cloud, like the humidity is so high, like in a shower, that you form this ice through the homogeneous process. So
but it doesn't, you don't get that all the time. It's just sometimes.
Right.
But the heterogeneous is more common.
Yes.
Well, I think Meta, think of your chocolate chip muffin. So that's heterogeneous, the chocolate chips, right? There's not many of them, but they're there and they're important. You know, without the chocolate chips in your muffin, it's homogeneous. So generally, if there's no abundance of particles, when the temperature drops below a certain level, minus 38 Celsius in this case, you get the water vapor within the air freezes into these tiny ice crystals, and there's many crystals spread throughout homogeneously. But the problem is they're very light, so the lifetime of the cloud is very long, and they're very reflective of infrared light. But so the idea of heterogeneous is there actually are aerosols there which will develop as nuclei for the ice, but they're few and far between. So that's a heterogeneous type situation. But the advantage is that they weigh a lot more, and they can descend. So the lifetime of the cloud will be a lot shorter. So I think the idea is to go to heterogeneity rather than homogeneity, and then that way the clouds, you can thin the cloud. Is that correct?
Yeah, that's perfect. Did you understand that, Meta?
Yeah, I think sort of.
Okay.
Pretty good. Keep going.
Yeah.
Okay.
So we wanted to find out the relative importance of these two mechanisms, heterogeneous and homogeneous. And that's what's been holding up the research. People don't know which is more important to these clouds, like which is more responsible for all the ice crystals. So
now why is it important that we have the ice crystals anyway? Because that's central to what you're trying to do, right?
it's just what nature does. So but
if you want to cool the planet, you can. Your technique involves doing things that require tampering with ice crystals, right?
Right. Yeah.
Okay, got it.
Yeah, you want to modify the cirrus clouds, right? You want them thinner so that there's less infrared.
To get a handle on which mechanism is more important or their relative importance, percentage-wise, we invoke this concept of extinction. We can separate out these two mechanisms if we relate the cloud properties to what's called the extinction coefficient. And extinction is basically, you can see it visually by which clouds are whiter, like these clouds. This is an example over the Sierra Nevada mountains. Reno is to the left, and the white clouds over the mountains have a higher extinction than the more diffuse clouds. And these diffuse clouds, having a low optical depth, when the optical depth is higher, the extinction is typically higher. And these heterogeneous cirrus clouds have a lower optical depth.
Optical depth means whether you can see through it or not.
Yeah, that's right.
Okay, and a high optical depth means you can see through it and it's vague, and a low optical depth means it looks opaque. Is that it?
Low optical depth is translucent. You can see through it.
Oh, so it's the opposite. Low optical depth is you can see through it. I had it backwards. Sorry.
Yeah. So like in this picture, the bright whiter clouds, they're more opaque. You can't see through them. They have a higher extinction and a higher optical depth.
Mm-hmm.
So that's the characteristic of homogeneous cirrus clouds. When you can't see through them very well, like if the sun is shining and you're looking through the cloud at the sun, you can barely see the sun, for example. But the other clouds, you don't even notice that there's a cloud there if you're just walking around, the sun shining right through the heterogeneous cirrus clouds. And anyway, you don't even notice that the sun is attenuated. So these are clouds called wave clouds that form over mountains, and these wave clouds produce a lot of the homogeneous cirrus clouds. So that's just familiar.
When you say a wave cloud, what is
wave
it?
cloud.
WHEY, like Milky
No.
Way? Uh-huh.
WAVE, like surfing. Surfing the waves at the beach.
Oh, wave clouds.
Yeah.
And okay, now explain again. What is a wave cloud?
So the mountains are forming a wave in the atmosphere so that winds blow over the mountains and the mountains force the air upwards.
Uh-huh.
And it creates a wave basically over the mountains, but it's a stationary wave. And clouds form in that wave, and that's what you see here, these white clouds.
Mm-hmm.
So anytime you lift the atmosphere, you're causing condensation a lot of the time, and that produces a cloud. If the relative humidity is high enough, it produces a cloud. These thinner clouds they will allow more thermal radiation to pass through them to outer space, and that'll cool the planet more. So if you convert those bright white clouds to those thinner, diffuse, translucent clouds, then more heat can escape and you can cool the planet.
Mm.
Either regionally or in a bigger way. So this is an example of, so if you wanted to do that, if you wanted to convert these white clouds to these thin clouds, you could introduce ice nuclei that are already available in nature. And this unseeded cloud is having mainly homogeneous ice nucleation. And these ice crystals are drawn here just to indicate that they're smaller. Like Paul was saying, this process of homogeneous ice nucleation produces a high concentration of tiny crystals. So they don't fall out as fast. So this arrow going downwards is small arrow, indicating that the fall velocities are small for these crystals. That makes the cloud last longer. So you have more cloud coverage with homogeneous ice nucleation. And they're thicker, so they trap more of the heat. They trap the heat and re-emit it back to Earth. So if you seeded this homogeneous cloud, then it produces larger ice crystals with higher fall velocities. The higher fall speeds make the lifetime of the clouds shorter, so you have less cloud coverage, and the cloud gets thinner as well. So the optical depth is less, the extinction is less in the cloud, and more heat escapes. So is that clear? The general idea?
Yeah.
Paul's already gone through it.
Now this
Yeah,
seeding thing, I'm not clear about what I think I've heard the word seeding, but elaborate on that, please.
So seeding is if you do it artificially. So nature's going to do seeding automatically. It's doing it all the time with mineral dust and other types of particles. Can be bacteria, it can be sea salt, it can be other things. So it has a whole, spectrum of ice nuclei available naturally. But there are places that don't get a lot of ice nuclei, and homogeneous ice nucleation would be more promoted in those areas. So you could seed those clouds artificially like they do in commercial cloud seeding operations.
Okay. What quick question? Could you explain why these clouds are stratified? There's air gaps between them. It's not it's not uniform cloud, but it's striations.
Oh, that was just the artist that did this. They're not really like that.
Okay.
Yeah, it's just the artist's conception, really.
Yeah. Okay. Okay. Thanks.
Uh-huh.
I've heard of seeding, so I assume that seeding is something that actually does go on maybe routinely in the world. Is this just like that? And it's just a special batch of clouds that you want to work on? Or how is it different from what's already been going on?
Well, that's a good question. Our research has just shown that we have pretty strong evidence, I think, that this is happening all the time. Nature is doing cirrus cloud thinning on its own.
Oh.
And I can show you the results of that research if you want, just one slide or two.
Mm-hmm.
But it shows that like there's some people that study mineral dust, and they do a global economy of mineral dust. What are the main source regions of mineral dust, and how does that transfer all around the world? How does that disperse from the deserts to affect other regions of the world? And what affects the cirrus clouds the most in the mid latitudes where we live is the Asian deserts. They get the mineral dust from the Asian deserts gets into the upper troposphere where the cirrus clouds are. And in the summertime, there's a lot more dust there than in the wintertime. And what we see is the homogeneously formed cirrus clouds are mostly in the wintertime in the mid latitudes and much less in the summertime. And we think that's because the change in mineral dust.
Mm.
So we think it's already happening naturally. And
But I've heard of people deliberately seeding clouds for many years.
Okay, so Meta, you're talking about weather modification schemes. So, like in China, for example, during the Olympic Games, they put silver iodide in the atmosphere to try to cause the clouds to rain out and not rain out over the Olympic Games. So silver iodide's been looked at for many years. That's the aerosol that you would put in. You can't use silver iodide here. Well, maybe you could, but there's other things that are much more effective. I think barium triiodide is
triiodide.
Yeah, so it's you would put that into the atmosphere with drones or with aircraft in the case of these cirrus clouds to cause the thinning. The other method, the silver iodide, which you're referring to, weather modification, is at much lower altitudes. Okay. And it's been done and experimented on by many different countries.
Yeah,
but not this method. So I can see. Are there any plans to do this soon? To do experiments?
No,
that you know.
There's no plans for any field experiments. And maybe you've been seeing the New York Times articles on marine cloud brightening, and
yes.
So there's a lot of pushback from the public on any kind of outdoor experimentation. So
well, wouldn't it be help allay their anxiety if you could say that nature does it anyway and you're just, giving it a little push?
Yeah, so nature does it, like, let's say in the summertime more than the winter. So if you were to do seeding, like Paul was saying, with bismuth triiodide or even silver iodide would work fine in these clouds. It's just more expensive with silver iodide. You could do that, what nature's already doing. You would have more heterogeneously formed cirrus clouds. And that would make the clouds thinner and their lifetime shorter. So
do we have an idea as to the we'd have to have extremely small dust particles in the summer that reach these high altitudes. Right?
That's right. Yeah, because the
And
heavier ones fall out.
right, and these little dust particles aren't, they're composed of many different minerals, right, depending on their source region. So,
Right.
so it's a
Potassium
different
feldspar
mechanism,
works well.
right? So they're just acting. It's just a physical. It's not a chemical thing. I mean, they're just there, little particles that the water vapor can condense on at high altitudes, right? So,
Right.
so does it really matter what the aerosol composition is? Isn't it more
Practical way, like if
Yeah.
you're talking about having drones or aircraft dispersing this material, then the payload becomes a factor. So you
right?
want tiny little particles that don't weigh much to be the
Yeah.
ice nuclei.
Right, but it's more of giving the surface there of a tiny aerosol as opposed to a chemical reaction. So you want silver iodide is non-toxic, as I assume the barium triiodide and other things that might be considered. It can't be toxic to plants or animals when it settles onto the surface of the earth.
Yeah, more testing would need to be done with bismuth triiodide, but
Right.
Pepto-Bismol is made of bismuth compound.
Yeah.
So,
What altitudes would we're talking about injection at the tropopause, which divides the lower and upper atmosphere, is at about 17-kilometer height in the tropics. It drops to about 7 kilometers at the poles. So are you talking about seeding maybe at 70 degrees latitude north, 80 degrees latitude north, and that would be at altitudes of say 10 kilometers or so? Is that the idea? You need drones?
Yeah, there is a seasonal change in this is the fraction of the darker the green is, the more the homogeneous type cirrus clouds there are. And I haven't gone through all the details of how we figure that out, but it's basically looking at extinction, and the extinction coefficient allows us to separate the two cloud types.
Okay.
I'm
sorry, say that again. The extinction.
Yeah, this is an example of how we separate the two cloud types. So what we have here is temperature on the y-axis, cloud temperature, and this is the extinction coefficient on the x-axis here in a log scale.
Okay, now the extinction coefficient is the length of time it takes for the clouds to be dispersed.
It's a measure of the blocking of light. So it's like a fog, for example, would have if you're driving through Thule fog and you can only see like a yard in front of your car, that's high extinction, because the light is not able to penetrate the cloud.
Okay.
But if you're just in a misty environment, that's low extinction. You can, when you're driving in your car, you can see way down the road because it's just a little mist in the air. So that's the same thing going on here. So again, here's that picture. Low extinction is demonstrated by these translucent clouds, and these more opaque clouds are high extinction. So that's what the x-axis is showing. And
the name of the game is to get low extinction clouds.
Yes.
All right, got it.
And what's plotted in each little square is the number concentration of ice crystals. So this is from the satellite remote sensing, those results. And we've shown the pink area is from homogeneous ice nucleation. We've proved that with what's called the Clausius-Clapeyron equation and the equation for homogeneous ice nucleation itself. It verifies that this pink region is ice produced by homogeneous nucleation. And on the blue over here, those are concentrations of crystals, say less than 50 per liter typically.
Okay,
And
now what does this prove? Yeah,
it proves that you can
they're
separate
pretty,
out
but, they're just pretty pictures to me. What does it mean?
it's shown by the Het and home there. So the Het nucleation process is on the left and the home nucleation process is on the right.
I'm trying to figure out what the meaning is of these things.
The meaning is, Meta, that they can detect regions that are heterogeneous and regions that are homogeneous. They can detect it naturally in cirrus cloud. Then they can talk about when they do their seeding, they'll be able to look for changes and see whether it's working or not.
Okay.
They can also monitor it from summer to winter, and they can see that in the summer there's a lot more heterogeneous clouds, cirrus clouds, and homogeneous, and they're attributing that to increased dust because the surface is drier in the winter and you get more dust up into the atmosphere. So this is metrics to measure what they're doing to ensure that they can measure what they're doing if and when they actually seed the cloud.
Okay. And this is new, or have you known this for many years?
No, this is brand new.
Okay.
Only
Good
the
for
last
you.
year.
Okay. Okay, now what else do we have to prove? You're going to show me.
We have to have a way like, here's a plot that shows, it's kind of visual and meaningful. If you've ever seen like these colors in a
No.
wave cloud, that's called iridescence. And it only forms when the crystals are really tiny, like less than a few microns in size, or around a few microns in size. So it's a process called diffraction that produces those colors, but it only does that when the tiny crystals are present, and you only get these tiny crystals with homogeneous ice nucleation. So we know for sure that the leading edge of this wave cloud is being produced by homogeneous nucleation. And the satellite results shown in the inset are like the sampling density of the clouds. So like in the red area or the pink areas, that's a high sampling density. But so most of the time, if you're in a satellite is looking at clouds below the cirrus clouds, it's sampling in that pink area. So very seldom, it's a rare occurrence when you get it into that blue area or green area. And the black triangles correspond to the region of pure homogeneous nucleation. So it shows that homogeneous nucleation is very rare in the atmosphere, but when it happens, it affects a whole lot of cloud. So that's the main point, is that it's a rare event, but it has a big impact.
Okay, now what do you need to find out before you've proved your point? In other words, there are people who think that your idea isn't going to work. In fact, I've interviewed a lady called Ulrika Lohman, and she has a whole tribe of people who are working with her, and they don't believe you, or they don't. I don't know, that's not a nice way to put it, but they don't agree that your approach is a solution.
Well, so, I saw your interview.
So what do you have to do to get the evidence that they would need to prove that you're right? And that's what I want to know.
I think all they need to do is read our paper when it comes out. If they don't believe the results, that's fine. But I think a majority of scientists would believe the results.
Oh, okay. And because what does your paper show that they didn't know about?
We did a radiation transfer modeling of in the Arctic at about 70 degrees north, and it's wintertime in the Arctic, so it's Arctic night. It's only long wave radiation happening. And this is a radiation transfer model initialized with satellite observations. So the plots on the right side are the ice water content with height that were observed from satellite. And then the one below that is the effective diameter of the cirrus cloud. It's a measure of particle size. It doesn't change very much. So the home and Het are indicated by the blue and the red colors. And so those are the two types of cloud. homogeneous and heterogeneous. And then when we do the modeling with the radiation transfer model, assuming that there's just cirrus clouds and no clouds below them, then we get the cloud radiative effect at the top of the atmosphere, and this plot on the left side, and it's looking at cirrus clouds having different cloud base heights. CBH is cloud base height. So they're having a thickness of about 1.4 kilometers in each case. So they're kind of like different layers in the atmosphere, but they're all showing similar amounts of cloud radiative effect. The difference between the blue dots and the red dots is what's important, because if you could seed the homogeneous clouds, you'd convert it into the red dot, cloud radiative effect. So that's how much cooling you could produce. And then the surface is in the middle. So that's surface cloud radiative effect is the middle plot. And this is for overcast conditions. So it's about 10 watts per square meter for overcast. Oh, and this is also between pure homogeneous and pure heterogeneous cirrus clouds. So 10 watts is a lot of energy, but that's the caveat is that we're looking at the difference between pure homogeneous and pure heterogeneous clouds. If you were to consider that, only about 32% of the Arctic clouds are homogeneous, then you would, divide that by, about a third, and you get about 3.2 watts per square meter at the surface for overcast conditions. And then if you consider that maybe it's not overcast, that only maybe a third of the sky is covered by cirrus cloud, then that reduces to 1 watt per square meter.
Okay, and this is very nice because there's always two effects of clouds, but there's no sunlight in this case because we're up in the Arctic and it's polar winter, right? So you're only you're having a large cooling effect on the planet, which is what you want, and you're not affecting, you're not allowing more sunlight in because we're in the polar night anyway.
Right.
Right.
And a lot of the tipping points are in the polar regions.
Yeah. Now is this is all in your paper that's going to be coming out? Is that correct?
There's a couple papers, so this one will be a separate paper. Yeah.
Okay. Great.
And so, and also this one on the right here is important because this is the amount of cloud radiative effect. It's really the difference between the surface and top of atmosphere. So if you take the top of atmosphere values, subtract the surface values, you get the atmospheric heat cooling effect. And this will affect the geopotential height of the atmosphere. So that can change the circulation pattern. And you might have heard of extreme weather events like caused by Arctic amplification. And that is, the Arctic amplification is warming up the Arctic much more than the rest of the world on average, maybe 3 times, 4 times higher. Mm-hmm. So in the wintertime, Arctic amplification is strongest. And if you do this cirrus cloud thinning, it would kind of beat down that Arctic amplification effect. And so the Arctic amplification may have already changed the jet stream. That's what some scientists are arguing. So to get it back to normal, you could do cirrus cloud thinning and restore a more pre-industrial circulation pattern so that the storm track was not as extreme in its undulations, the wavy jet stream effect. So a huge amount of research would have to be done on that, but that's a possibility that we're looking at. That's it for the radiation part. I could show you like the natural cirrus cloud thinning.
Quickly, yeah. You're going to show us what nature does, huh?
Yeah. This is the fraction of cirrus clouds that are microphysically dominated by homogeneous ice nucleation, meaning that the cloud properties are strongly affected by homogeneous ice nucleation. And so the darker green areas are having more homogeneously affected cirrus clouds, and the white areas are having more mostly heterogeneous cirrus clouds. So the tropics is having very little, based on our satellite retrieval scheme. We're not able to measure the thunderstorms, like the really thick clouds associated with thunderstorms. We can only measure up to an optical depth of 3. So that's why the tropics doesn't have much homogeneous nucleation, because we're only seeing the anvil clouds away from the thunderstorms. Anyway, that's kind of a
Now, what does this tell us in terms of policy? If we're going to do something, we learn to do what from this?
Yeah, I'm getting to that. So,
okay.
What we see is on the left, it's wintertime, and on the right side, it's summertime. We're at boreal summer. So June, July, August on the right. And there's a lot more dust produced in the atmosphere from the winds over the deserts of the East Asian deserts, Gobi Desert, Taklamakan Desert, and so on. So those regions are unique in that they transport the dust to high levels in the atmosphere, because it gets involved in frontal systems and thermal convection and stuff that can transport the dust higher. So that dust affects the cirrus clouds. And these dust measurements correspond to 200 to 400 millibars, or sometimes called hectopascals, in the atmosphere. That's upper troposphere, where the cirrus clouds reside. So this is a paper by Koch et al. From 2021 in the Atmospheric Chemistry and Physics Journal. And they have, in their supplementary material, they show the seasonal changes in dust concentration at all levels in the atmosphere. So it's a very good study that allowed us to relate our results to what's going on with dust.
Now let me make sure I got it. The left side is the summer and the right side is the winter, huh?
The right side is the summer and the left side is the winter for northern hemisphere.
Left side is the winter, the right side is the summer. And from this, you have less dust.
In the wintertime, we have less dust.
And therefore, it's easier to get rid of it because there's less of it.
So you get more homogeneously produced cirrus clouds when there's less dust, because dust is ice nuclei. So it's going to produce heterogeneous ice nucleation everywhere it goes. So when you have a lot of dust, you have a lot of heterogeneously formed cirrus clouds. And if you see, like, between 30 and 60 degree north in the June, July, August, there's very little green there. So that means mostly heterogeneous cirrus clouds.
Okay, so as far as cirrus cloud thinning goes, you would want to do it mostly in the wintertime, is that correct? When
Correct.
There was the natural dust being produced from dust clouds.
Correct. That's one reason.
And you would also do it in the high latitude regions because you're not going to interfere with the with shortwave radiation processes, because it's complete darkness up there. So in the southern hemisphere, winter, would you do the same thing? Would you just alternate hemispheres?
Yeah.
So you could do this cirrus cloud thinning aerosol injection year round.
Right. Right. Exactly.
Right. Okay.
Yeah, you could just switch hemispheres.
Right.
We see the same phenomena occurring over the Southern Ocean. When there's more dust, you have more heterogeneously formed cirrus, and then
Yeah, but in the southern hemisphere, you wouldn't get much seasonal variation in the amount of dust, would you?
exactly,
Because you
yeah.
don't have huge dust deserts down there producing as sources of dust.
Yeah, it's 30 to 60 degrees south mostly, so you don't have
Yeah.
much land in that latitude band.
I have had this other person say she doesn't think that what you're doing is going to work. And now you say that you've got evidence that's going to probably even convince her if she'll look at it.
So,
What has happened? What have you discovered here that you've shown us that she didn't know that should make the difference?
so her models predict mostly heterogeneously formed cirrus clouds. So what's different here is we're finding there's a lot more homogeneously produced cirrus clouds. And when we look at the radiative impact, it looks like about half of the radiative impact is due to the homogeneously produced cirrus clouds.
So that means you have more stuff to work with to get to make this work, right?
Yeah, the more home cirrus clouds.
Uh-huh. Okay.
Yeah, we have a lot more than they realized.
And therefore, any seeding that's done will have a much larger effect because it's a homogeneously, at least half of it. The forcing is from the homogeneous. So you
Right.
can make those 50% homogeneous more heterogeneous. You have a huge impact on cooling.
Well, that's yeah. So one caveat here is that it may not have a huge impact on cooling because we're only looking at 1 watt per square meter, and it's significant, but it's not like a sledgehammer on the climate system at all.
Oh, that's one of the things I was going to ask you is at the most, how much of our global warming problem could you solve with this thing?
I
Not
think
that much.
1 watt would maybe get us close to pre-industrial right now if we could just turn it on. So it could remove most of the problem that we have right now, but we have more problem in the pipeline, like Jim Hansen is saying.
And you can turn it on and turn it off extremely quickly. In order for the effect to be effective over a period of time, you have to do continuous seeding, right? It's not a one-of. You just have to, every time the northern hemisphere goes into complete darkness in the Arctic regions, you go seed there. When the winters, when we go to northern hemisphere summer, southern hemisphere winter, then you change your drones or aircraft to seed in around Antarctica.
Yeah. And
so you have to keep doing it.
Correct in inferring then that means that it isn't that there's a whole reservoir of heat and we're going to let some of it out and therefore that little bit of release is going to help us for a long time. It's that there's a continuous coming in and moving out, and if you stop interfering with the flow in and out, there's no cumulative benefit, right? You have to keep doing it in order to get the ongoing effect. Is that right?
Yeah, that's what Paul is saying. You have to keep seeding continuously. So it's a big commitment, and you might have to do that for 100 years or so.
Right.
So
okay. Well, now we have a lot of other competing innovations that people are proposing, and I guess you need to say why you think your way is the best. Is it the cheapest?
No, I'm not trying to say it's the best or anything. So, I'm a scientist, so I just try to do the research and let other people decide what's best. So what I wanted to point out also is that this whole idea could be a red herring if you have low clouds below the cirrus clouds, like water clouds, and those water clouds would neutralize the cooling effect.
Right, but you generally don't have too many of those, if we're in complete darkness, say in the Arctic winter.
Yeah,
because it's the poles are basically deserts compared to the rest of the planet. It's very dry. There's very little water vapor in the air.
Yes, that's what we found based on the literature that we looked at. Yeah,
So it's the ideal regions to do this.
it seems like that. Yeah.
Now, all right, now what are your main contenders for the seeding material then? Are we talking about barium triiodide? Is that your favorite,
Yeah.
or are there other ones?
I think Meta had, when you had Ulrike Lohmann and Blas Gasparini on,
Mhm.
and they talked about another idea that's related to this called mixed phase cloud thinning.
I'm going to actually have that guy Villanueva or something.
Yeah,
And
Villanueva.
he's the lead author on that other paper, but it is apparently their team that's done it.
Yeah.
So they are very familiar with it.
So I mentioned them because of what Paul was asking on seeding material. If you use silver iodide, you could do the mixed phase cloud thinning, and you could also do the cirrus cloud thinning. So it might be two birds with one stone. You do both of those, cirrus cloud, mixed phase cloud, get them all glaciated. In cirrus, it's already glaciated, so you're just changing the formation process. But
What'd you call it? Gluchy? What'd you call it?
Glaciating, that means turning it all to ice. So the mixed phase clouds are a mixture of liquid and ice. And when you seed them with silver iodide, they turn into pure ice clouds.
Yeah.
And that's what's allowing that process to cool the planet. Is that the liquid in the cloud is trapping a lot more heat than if it was pure ice, it would allow more heat to escape. So
okay, now I don't quite. I haven't even talked to anybody about that other thing, but I take it when they say that your system won't work and this mixed phase
it's
cloud.
just Ulrike Lohmann saying that. Blas doesn't say that.
No,
it's just one person, Meta. I mean, there's always going to be naysayers. It doesn't. So I don't think we should focus on one person saying it won't work. I mean,
fine.
In your interview with Blas, he actually said that he said he thinks the cirrus thinning idea could work, but what he said was there's not as much bang for your buck with the cirrus cloud thinning possibly, and I agree with that.
Okay.
It's not a real strong technique from what we can tell.
Okay.
So
But
Blas
now,
agrees with me.
you don't disagree with their claim that this other thing, this mixed cloud thinning, would work. You think both yours and theirs would work, but maybe they'd have more bang for the buck than yours?
Yeah, it could.
Okay.
I don't know. I think that research is still pending to do on that.
Okay. So what more do you need to do to satisfy the critics? And then what more do you need? I mean, the sophisticated critics who don't believe in your method. And what more do you need to do to satisfy people who are just scared of geoengineering and as a general thing? Is there any reason to think they have anything real to be afraid of? What might happen? What might go wrong?
I think the main concern would be changing the circulation pattern, because you're changing the geopotential heights when you do potentially you're changing the geopotential heights, but that could be for restoring the atmospheric circulation to pre-industrial pattern. So it might be a good thing. But that's something you'd have to be careful with.
I didn't know that there'd been a change. We've already changed the circulatory patterns, and it might be a good thing to go back to the way it was.
Meta, you're familiar with Jennifer Francis and all of her work on the wavy jet streams. Of course, we've changed the jet streams. They've become much wavier. We're getting more and more extreme weather events, right? It's all Jennifer Francis's work.
Okay.
Right? On the waviness of the jet streams. That's what we're meaning by the overall circulation patterns of the planet, the jet streams. So when you hear of general circulation patterns, think jet streams, and we know how they've changed to our detriment. So what David is saying is that cloud seeding in, say, the high Arctic could actually straighten out the jet streams and bring them towards where they were before they started going haywire and wavy, which would be
Yeah.
a very positive thing if we could actually do that. We would cut back on extreme weather events. It would probably be the most significant factor from using this method, which I don't hear about mixed phase seeding having the potential to do that. I haven't seen that video where you interviewed the mixed phase people, but presumably it's at lower.
No, I haven't interviewed them yet. They've talked about
Okay.
Lohman and Blas Gasparini talked about both David's system and this alternative.
Okay.
They mentioned it, and so that's what made me think, since they believe in it, how they're going to get the guy. And
Okay.
Yeah.
Okay, so do we know what altitudes and what latitudes the mixed phase seeding is that where that work is supposed to occur? Are we talking about seeding the
same-
fold?
It's the same as the Cirrus cloud thing. It's in the wintertime in the Arctic.
Okay, but lower
altitude.
elevations, right?
Yeah. Uh-huh.
Could you combine the two approaches? Have one plane go
Yes.
east high and working out cirrus clouds, and go back west working on the other mixed phase clouds or whatever.
That's what I'm suggesting. Yeah.
Yeah?
Uh-huh.
To save some bucks. Okay.
Yeah, two birds with one stone.
Yeah. Okay. Would this, in practical terms, if you talk to, people who have to buy airplanes and figure out where to get the kind of dust or whatever you want to do the seeding, what are their concerns? Are they
Non-toxic.
thinking that anything is feasible, or have you got to the point that you are even talking to them, or do they care about what you're doing?
I haven't even looked into that because my focus has just been on the science, the cirrus cloud formation process. Before going into all these engineering details, I feel it's wisest to find out the basic physics of how the clouds work, how they form through these mechanisms. And
Well,
once we know that, we can move forward.
Maybe Paul can give a better guess, because you're looking at these.
Okay. Well, let me ask a couple of related questions. We're talking about upper atmosphere physics. We're talking about what's going on at the tropopause, which is where the troposphere ends. So temperature is highest at the surface of the Earth, and then it decreases in the troposphere, and it reaches a point where it reaches the coldest point, and then it's kind of stable, doesn't drop, doesn't increase or decrease as you go up. And as you go into the stratosphere, then temperature starts rising with elevation. Okay, so that's basic layers of the atmosphere.
Right.
So I have a question. We know that global warming is increasing the troposphere and decreasing the stratosphere temperature. Therefore, it's raising the level at which the tropopause occurs, which is the layer between the troposphere and stratosphere. Okay, the level is rising about 5 or 6 meters a year. It's been doing that for the last 3 or 4 decades. So there are definite changes. There was a very interesting talk recently about the strength of tropical storms being greatly increased, having to go to category 6, category 7, perhaps, I'm recommending. Michael Mann was talking about the simple Carnot heat engine model of the atmosphere, where one temperature reservoir is the surface of the ocean. It's about 300 Kelvin or 27 degrees Celsius. The other reservoir is the upper atmosphere, which is about 200 Kelvin or minus 57 Celsius. Now, we're getting stronger tropical storms because we're raising the sea surface temperature, maybe a degree in the last century. But my question got me thinking, his paper and this work, which takes place at the same altitudes that Mann was talking about, has the temperature of the tropopause changed? in the last couple hundred years, say? We know the stratosphere is getting colder. Is the troposphere actually getting colder? And if it is, and the change is more than, and I've done some research and I've seen that it's actually colder by about 2 to 3 degrees Celsius. Now, it seems that cooling of that tropopause layer would actually have more effect on increasing the strength of these hurricanes than the actual heating of the sea surface temperature. And yet nobody is talking about that or considering it. So have you looked at those? And that depends, and the forming of cirrus cloud is very important in that region. And also the amount of water vapor transported to the stratosphere from the troposphere is very dependent on those temperatures and the height of the tropopause in those regions. So there's a lot of physics in here which we don't understand. So I guess I'm not expecting an answer from you, David, but consider that maybe the cooling of the upper atmosphere layers is strengthening tropical storms. If you see any data or anything to that effect, let me know, because I read Michael Mann's recent paper. I've read 3 or 4 papers published in the last couple of years on the temperature of the tropopause and how it affects the formation of cirrus clouds, how it affects the transport of materials to the upper atmosphere. But I haven't had that question answered. It appears to me that the graphs that I've managed to acquire show that, say, in the last 40 years, the tropopause temperature has shifted downwards, cooler by, perhaps up to 3 degrees Celsius. And if that's true, then again, that's a major factor why these hurricanes are getting much, much stronger. And also it changes, the number and distribution and characteristics of these cirrus clouds. Like, they're being modified already by climate change. So, the biggest effect, I say, is an increase of 5 to 6 meters in height of where these clouds are located, where the tropopause is located. So these are all factors. If you come across any information on this, we should talk.
Yeah, that's really interesting. So you're Michael Mann's arguing for like a Carnot cycle of the atmosphere, basically, and it's the heat differential between the tropopause and the ocean.
Yes, and it's not his work. He's basing his he had a paper in just that came out a few months ago, February of this year, or it was an article or letter, and he showed that diagram of the Carnot heat engine model for the atmosphere. And that was based on work that was from a paper of a couple of years previous.
Okay, so
it's just an interesting way of looking at things. And if you can take that model, we're actually changing the temperature of both reservoirs. Mann and the original paper only talked about changing the temperature of the sea surface temperature, ocean temperature, that reservoir, and that's about 1 degree Celsius rise in 100 years. Nobody's really talked about changing the cold reservoir temperature. And I think the reason is that the tropopause is generally thought to have a fixed temperature, right? It's where the temperature stays constant with altitude for over, maybe between, say, 11 and 18 kilometers in height. And then after that, you're into the stratosphere, and then the temperature starts to rise as you go higher up. Right. But so that fixed temperature. So the question is, we know that the height of the tropopause is definitely increasing by that 5 to 6 meters per year over the last, so 50 to 60 meters a decade over the last, say, 3 or 4 decades. Right. We know that, and we know, and that effect is because of the overall heating is expanding the troposphere. It expands the air, and we're also getting stratospheric cooling. Right, because one of the effects being that our cirrus clouds and everything else are reflecting the infrared. The infrared doesn't allow it to go up into the stratosphere to cause heating, so it's causing a cooling there. Also, there's ozone changes in the stratosphere that we know about and have been occurring for many years. So there's a lot of different effects in this, but I think if it's true that the cold reservoir of that Carnot engine is 2 to 3 degrees colder, the warm part is 1 degree warmer. The temperature difference is what's key to the strength of all of these storms. So that temperature difference could actually be the 1 degree plus, 3 degrees. It could be as high as 4 degrees different over the last century, right? And that would have a
Yeah.
massive effect on storms, because we're talking about, like the argument is that for every degree increase in the lower temperature, it's causing a 12% increase in the wind velocity that can be generated in these storms. If you look at the power density, that depends on the cube of the wind velocity. So that's a 40% increase in strength of, say, hurricanes now compared to, say, 3 or 4 decades ago. Right? But nobody's
Yeah.
considering the change. Everybody's considering the upper stratosphere, the tropopause temperature is constant. And we know it's not constant,
Yeah.
according to the research that I've been able to find, but nobody's making that connection yet. So
Well, climate
anyway,
science predicts.
anyway, I'm going to
rising.
do a video. I'm going to do a video later today on all of these all of these tropopause changes, because I think I have enough material, enough research to do that. So
That would be very
you have-
interesting.
Do you have, Paul, do you have any other question you need to
I
ask?
do have a question.
Okay.
Okay, so let's give you, say, $5 million. Okay, so do some experiments. Deploy. What are you going to do? Get some drones and get some barium triiodide, or what can you do to demonstrate that this thing's going to work? Or what would you do? Like, what would you? I mean, I know that you're looking at the science, but I mean, you need to involve some engineers. Is it better to use drones or better to use some aircraft? I mean, you need specially designed aircraft. Well, I guess if you're going 10 or 11 kilometers, you can do that with most commercial aircraft, I think.
Yeah.
So if you're doing it in the high Arctic, you'd go to about 80 degrees north and start deploying this stuff in the winter, and then you'd be monitoring the results by satellite. Or I mean, what's sort of the next steps to deploy this?
I think a lot of scientists think that drones might be a better option, because if you're talking about putting in ice nuclei material into the kerosene of the jet engines and all that, it gets really complicated, and the airline industry probably wouldn't go for that. You might have a separate fleet of aircraft to do that, but anyway, drones would probably be cheaper.
Do we have drones that go up that high and that are large
Yeah.
enough, though?
Yeah, I heard we do.
Okay. Talking about military drones, like
Uh-huh.
Predator. Are you talking about military drones? Like, we don't know their capabilities necessarily.
Yeah, I don't really know that much
Yeah.
about the drone industry, but I think
Okay.
you have them.
Okay.
So
Okay.
that could be explored. But for an experiment, I guess you could look at a region of the world, like over the Rocky Mountains, where there's a lot of these home cirrus clouds forming, and see if you can change them to het cirrus clouds. And
What about high altitude balloons? Wouldn't they be better? You could carry huge payloads and they could stay up there
yeah,
for a long period of time, the whole Arctic winter, and move around. And
yeah, like a
Deploy.
tethered balloon type of thing.
well, it free flying balloon, but I guess tethered if you need. Well, if you put it at a certain latitude in the Arctic, it would just circulate around the Arctic. It wouldn't change latitude that much, I
Right.
would think. So you'd have some propulsion on this balloon, like more like a dirigible or something.
Yeah.
I'm thinking it was World War II, Zeppelin or something like that.
Yeah.
Being, I think the technology will be improving for that type of delivery system, because I've been recommending that many northern Canadian communities that are relying on ice roads, which are no longer forming in the winter because it's too warm. The best way to supply these communities would be through heavy lift balloons, basically, or zeppelins. Right?
Yeah.
It would be far cheaper than building permanent roads, hundreds of kilometers, hundreds of miles through the northern lands of Canada to access a remote village that needs supplies and that has like several hundred people in the community. That's it. Building an ice road is extremely expensive. So using balloons, unless there's Anyway, I think the technology, that's something to look at. I think you're at the stage where, in order to promote the idea of cirrus cloud thing, I think you need to get some engineering people involved and say, well, how would we actually do this? What would it cost us? And what would be the cost per unit of cooling? And then you can compare your idea, as Meta was saying, how does it compare to other ideas, right? And your remarks were, well, it might not be the cheapest or most effective, but we don't know that unless you actually sort of cost out what it might be, and then all you need to do is
if it had the added benefit of affecting the cloud, the
jet stream, yeah.
Mhm.
Yeah, and then you don't need public buy-in from everybody. All you need is to convince a billionaire to put up some cash so that you can actually go and do it.
Yeah, I did a calculation on how much it would cost with bismuth triiodide a long time ago.
Yeah,
And it was really cheap. Like,
yeah, I think it is. Yeah,
the aerosol size is what's critical. So it's like 0.1 micron for these ice nuclei. The average particle size for ice nuclei with bismuth triiodide and silver iodide is around 0.1 microns. It's really, really small. So you get a lot of bang for your buck when you want to, say you have a kilogram of seeding material. It goes a long way.
Right. And do you have some sort of way of producing the very small particles once you have the material? Like an atomizer or whatever?
Right. They have these generators they put on the mountain ridge along the Sierra Nevada mountains that where I live. Desert Research Institute does that operational cloud seeding operations all the time. I guess they have a solution that contains silver iodide, and that gets burned in these generators that produces that fine distribution, really tiny particles.
Thank you so much, David.
You're welcome.
And Paul too, because
thank you, Paul. Yeah.
Well, thank you. It was great hearing about your work. I think it's got a lot of potential.
Thank you. Yeah. Oh, one little thing I wanted to mention is that even though there's less homogeneously formed cirrus clouds, their optical thickness is a lot more, and that's why their radiative impact is a lot bigger than the heterogeneous. So that's why about half of the radiative effect of all cirrus clouds is through the homogeneous cirrus clouds because of their optical thickness. So
okay,
all the
thank you for all of that, and we'll be back in touch because obviously this is just getting started, a long way ahead.
Yeah, I think so.
Good for you. Thank you so much, David and Paul.
You're welcome.
Thank you. Okay.
Bye-bye.
Project Save the World produces these forums. This is episode number 615. You can find all 600 plus forums on our website. Just go to savetheworld.ca and look at the scroll window on the home page. You can scroll around until you find a topic that interests you, and then click and you can watch the forum right there. Project Save the World also produces a short course for people who want to become leaders in the movement to repair the climate. This course is available free of charge on the online learning platform Udemy. It consists of 5 short lessons about the use of soil amendments as a way of removing carbon from the atmosphere and sequestering it in the earth, thereby improving agriculture and increasing the world's food production while reducing the need for synthetic fertilizers. The course is entitled Become a Climate Change Influencer, and you can learn more about it at this link, www.udemy.com/course/become-a-climate-change-influencer. Finally, Project Save the World also produces a quarterly online publication, Peace Magazine, which now serves as a free of charge newsletter to help mobilize knowledge about 6 global threats to humankind. We gladly email the magazine as a PDF or a link to any interested organization in the world that works to prevent a global catastrophe involving war and weapons, global warming, famine, pandemics, radioactive contamination, or cyber risks. Just email us at office@peacemagazine.org and we'll add your group's email address without charge to our list. For individual subscriptions at $20 Canadian per year, go to pressreader.com on your browser and search for Peace Magazine.